Hello, I'm Bill Wake. We're here working on a program to compare tunes for similarity, and now we're getting into the real clustering and kind of automatically grouping tunes that seem to be similar. So we've just finished some work on the clustering algorithm. I hope to get to the dendograms part of that today, which is drawing a sort of a tree that represents the clustering. But we have some more work to do, testing and I guess testing it at least before we start doing the UI kind of stuff, the dendogram stuff. Okay, there's probably math to do before we get to drawing it. All right, let's see where we are. I think we wrote a test. Yeah, we wrote a test without completing it. Okay, so I believe we've got our clustering algorithm together. So let me bring up what we have. Okay, so the core of the algorithm, it's this single linkage clustering. I think that's the one I'm on here. Okay, so the algorithm is we're basically going to find the two pairs that are closest, or we put everything in its own cluster to start with. So I've got 39 versions of Nascalan. I'm going to start with 39 nodes. Then I'm going to go in and find out for every pair of these nodes, which two are the closest. I'm going to group those into a cluster. And then the next thing I'll do is I'll look for the next two clusters, the one I just made or any other pair of clusters, the next closest things. Okay, maybe that's a different pair. And I look for the next one. Maybe that merges the first four and leaves a bunch of others, But we go through this cycle. So notice this, all objects in one cluster stop, else go to step 2. So it's kind of a while there are more cluster, more than one cluster. Okay, so everything starts off in its own cluster. Then we find the closest pairs and group them into a new cluster, n+1. Okay, we set a level, which we'll come back to. And then we update our matrix of closeness. We delete the rows we just clustered together. We add a new row for the new cluster. And then we have to worry about the distance from the new cluster to all the other clusters. And that, and then we repeat until we run out of nodes. Okay. That distance is defined as given a cluster that was formed from X and Y, which are themselves clusters, find any element in X, any element in Y, find the pair with the smallest distance. So it's sort of clustering based on the least distance between any nodes within an existing cluster. All right, and let's see it in code here. Okay, so we make a map with. Let's see. We find out. Okay, we're coming in, and this. Let's see. Let's go to the constructor. Okay, we're finding the maximum. I guess we've assumed we've already done it. Yeah, so go to our tests. Right, so we... these tests. Okay. I've still got this all in the same file. Okay, no wonder I'm confused. All right, so we cluster elements. We put them in with indexes 0, 1. So we're just going through the existing single elements. We're going to add them. So we turn each element into a 1-element cluster. Okay, this is element 3, element 4. Add them in together and then ask for the clustered value. Okay, so the initial state, it assumes we've put them in properly. I think that's a mistake, but we'll deal with that later. Okay, so we go find what's the highest number we have. We go through the matrix and ask it, what's your maximum sequence number? And then we're going to increment before we use it. So, okay, we find the best matched pair. Okay, so we go through everything in the cluster, all clusters, find the two that come up with the best score. increment this M sequence number, then we calculate the distance between those two. We actually already did calculate it here, so that's a little bit of extra work, but conceptually it doesn't matter. It's a constant relative to what we have. So we calculate the distance, and then we store the new cluster. We keep track of the sequence number, the distance, and the contents. Okay, these two clusters. And then we remove the old ones and add the new one. Okay, so every time through the loop, we're removing 2, adding 1. So each time through the loop, it gets 1 smaller. And eventually, the matrix count will be 1, assuming it starts off bigger than 1. Okay, and then, so, I mean, that to me is pretty close to the algorithm we had. Can probably tighten it up a little somewhere, but you know, we find the most similar cluster, we increment M, merge them, add the new row, delete the old one. Okay, that's pretty good. Okay, I mean, I'm happy there. I'm maybe not as happy with this part. Okay, how do you find that best pair? Well, we're going to run through basically all combinations of 2 entries. And for each, we're only going to keep the ones where the first is less than the second. So if it was numbered, it'd be 1. We wouldn't do 1, 1. We'd start with 1, 2. Well, let's take row 2. We wouldn't do 2, 1 or 2, 2 because they're less than or equal. We only keep the ones that are, they're greater or equal. So we only keep the ones that are less than. Does that make sense? But we're going to get 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 2, 2, 3, 2, 3, 2, 4, 2, 5, 3, 4, 3, 5, 4, 5. Okay. This may do that already. I think when we did a little look at it debugging wise, it looked like combinations took care of this part of things. I don't know if that's a guarantee or not. All right. And then what we do, we just, we find the numbers, the sequence numbers, and we get the distance from the first one to the next one and find the least distance. Okay. It's a little overcomplicated because we got to track the best pair and the least distance. But once we do, we get through the loop, we've matched all the combinations, and we return a pair of the 2 elements of the best pair. Okay, the 2 cluster items. All right. And I think the other one that's a little complicated is distance from one cluster to the other. Okay, and really we're just saying find every combination of one with the other, and I think that's right. Yeah, so we have all the nodes or elements from one node, all the elements from another. We want to know the least distance for any of those, and we can run through that Cartesian product, map each one to their distance, and then find the minimum distance. Okay, so I mean, it's not horrible. The rest of it's pretty easy. Add and remove and count. You know, they practically just do that. Okay. So I don't know. It's not a, you know, I mean, even with tests, 200 lines, give or take. Okay. Now, where we left off, I think the algorithm looks like enough of a match to me that I'm pretty confident in it, but I want to do a real test. So here I have these numbers, and we're grouping them by just distance between them. So the distance from 1 to 2 is 1, 2 minus 1, absolute value of 1 minus 2 or 2 minus 1, distance of 1, distance of 7, 1, 1, 38, 10, and 1. All right, but I would say these two should pair together. These 3 should pair together in some combination. These 3 should pair together in some combination. And then we look and say, okay, among these clusters, 1, 2, 3 is closer to 10, 11, 12 than it is to 50 or 60. And so those two should cluster together. And then 50 is closer to 60 than it is to 12. So I would think these 3 would cluster together. And then finally, 2 clusters join and everything's in there. All right, now the sequence numbers in order. Okay. Well, gosh, that doesn't seem like a big deal. We want to create elements like this with these numbers in order. Okay, so I think I can take, let's take, how about sequence numbers? And let's take 0 less than values.count. Okay, so 3, 6, 7, 8, 9 values. So it should be 0 through 8, the indexes of those things. Okay. And now we'll take sequence numbers for each. And we're going to build up a cluster like this. Cluster element. Okay, yeah, this is almost it. Okay, cluster element. Well, let's take $0 is the sequence number, 0 is the default distance, and the value is value sub $0. Okay, so that's the index we're after. All right, we put them in the matrix, we cluster them, and I just grabbed this. It's not relevant here. Okay, the result is a matrix with one item. Okay, now do we have a way to get it out of the matrix? Oh, what does clustered do? Does it give us it gives us the element? Okay, so we can ask for the clustered value. All right, yeah, this is a cluster. All right, so now let's check result dot, I don't know, sequence number is not the thing to check. But we can check result.elements, which is the set of all elements. Let's make this a set. Oh no, that won't help. We'll do it down here. Okay, so set of int, giving it values. Okay, so in the end, if it clusters correctly, the contents should be exactly these. Okay, this doesn't get the structure. It just makes sure all the values are in the cluster. All right, and so I'm going to run that test, and I think it should pass. All right, it doesn't check that the clusters work, and we'll have to do that next. Let's just print result. I don't know what we'll print from it because we've never added anything for that. All right, but I expect it to pass, and I expect it to print something. Now, this is kind of slow. I haven't even started tests yet. Okay, never mind. Okay, it did pass. Did it print? Oh, yeah. Okay. Well, so 16, the first number is the sequence number. So that tells me like these are 0 through 8, and then 9, 10, 11, 12, 13, 14, 15, and 16. Okay. So yeah, I believe it seeing it. Let's check that. Result.sequence number is 16. And that's a direct result of the number of clusters, and they it varies depending on their closeness and stuff. So there's no this isn't some like count or anything. This is a result of the actual clustered sets. Okay, and a different set might have a different number. All right, now I don't know what to do to get there. So see, 16 holds a cluster that's, well, it's got a distance of 7, which seems odd to me. I would think a lot of distances would be relatively, oh, maybe 7 is, it is based on the numbers. Okay, so it's not my 0 to 1.0 thing. All right. I think what I want to do is I want to define a function that produces like a list kind of thing. Okay. Let's define it. Okay. So what I really expect, and let's see if we can make this work. Okay. I expect a result dot, well, I expect format of result, which we haven't written, to be a string. And the string is going to be, well, I think 1, 2 is a cluster. And then that's going to cluster with 3. I guess I put spacing after, but before I add a number. 3 parentheses, and then 10, 11, 12 is a cluster. All right, let's put this on a new line. Okay, 10, 11, 12 is a cluster. And then 60, 61. And then I think 50 should cluster with them. And then, okay, I think 1, 2, 3 is closer to 10, 11, 12 than it is to 50. So that should cluster. And then I've got 2 blocks left, so the whole thing should be the rest. Okay. Now, format is going to be a little recursive routine that walks through a cluster. Okay, so let's define that. Function format, and I don't think it's easy. All right, it's, I don't think it's trivial, I should say. It takes a cluster. Let's just make it int and make our life easier. Returns a string. Okay, so all we can do is look at cluster. Switch cluster, and then one case is element. I think I can pull out, well, I don't care what its sequence number is. I don't care what its level is. I just care what its value is. Okay, so that's getting at the number that's stored in the value. Okay, what can you do there? Well, I'll just say print value, and then I'm just going to get this thing, the shape of it first. The other case is cluster. Ignore sequence number. Ignore level. And then this is let clusters. You know, it's a set, so I don't have control over the order of things. We'll deal with that later. All right, and then what I want to do is recursively do things. Okay, so I'm going to return a string. Well, let's let results is format. let's take clusters dot sorted by a function. I think I thought I had another sort that was just that. Okay, let's just take it clusters. We're going to map each one to cluster format of cluster. Okay. Oops. Yeah. Okay, take clusters, map them to format. Is it joined by? Space. Okay, is that a string? Unjoined by collection. Okay. Okay, joined by this. Is it happy with results? No. I don't know if I can just do string of results. Plus a right parent. Okay, well, let's see. All right, so this case is simple. If it's a number, just return the number. If it's not a number, then it's a list of clusters, and we're going to take each one of those as interiors, separate them by spaces. Format them, separate them by spaces, and then put parens around the result. And we'll see what we get. And then I think I will say print format of result here just to get myself confident. Now, I didn't sort things, so it is likely to be wrong. But I think hopefully it comes out looking somewhat reasonable. Okay, so 312, 12 to 11, 50. It structurally looks right. It's certainly an acceptable answer for that. It's really a question about what's the best way to write this thing. Because these are sets of things, it's certainly acceptable to put this in front. And I think it'll be consistent. Same here. Okay, is that what we have? 3 lefts, 3, 1, 2 rights, space here. Appending 2 things together, space here probably. No? Oh yeah, okay. 12 to 11. Okay, let's try it again. One failure. Oh, 1, 2, 3, 12, 11, 10. Oh, so it's not consistent. Well, this isn't a good testing problem. Certainly, both these answers are acceptable. The question is, can I force this? Yeah, I mean, it's a nice handy way to write a tree. I don't have the tools to make it as useful. And the funny thing is, it's sort of a, usually you have trees and the order matters. And in this case, it doesn't. And that's weird, unusual, I should say. So what I can do, like somehow I have to force, I'm trying to match sort of an unordered tree to another unordered tree, really. Now, I don't know if I can, let me try it with sorted. Well, actually, if I sorted, how about if I map them and then sort them? Now, there we go, sorted with no argument. Okay. Then the parenthesized one comes out ahead of the unparenthesized. So I think it will be my original order: 1, 2, 3, 10, 11, 12, 50, 60, 61. Okay, let's try that. No, not quite. 1, 2, 3. Oh, it did swapped it again. But I think it's going to be consistent now. Oh no, that is consistent. This is bigger as a string than this. I posted probably the thing I've done on Mastodon. It got me the most reprints, but it was a Ben Franklin quote that's something like, "It's what a wonderful thing it is to be a rational creature, because then you can devise any reason you want, basically, convince yourself of anything, more or less." But I think if I take 1, 2 in parentheses versus 3, it sorts earlier because paren is less than a digit. Same thing here. Same thing here, even though the number is bigger. It's not looking at the number because it's not parenthesized. We could imagine, well, it's not a great solution, because if we'd like to be, if we had 60, 61 versus like 50, 51, okay, 50, 51 should sort first, unless we had 100, how about 160 versus 161, and it looks smaller sorted as a string, but it's bigger numerically, so it really is just enough for our purposes and not much more. All right, now this should pass, and it should pass consistently. We'll run it 3 times just to make sure. Oh, man, what is it? 1, 2, 3, 4. 1, 2, 3. 10, my space somewhere? Oh, I got 3 parens. Is that right? 1, 2, 3, 4. 3, 2, 3, 4. 3, 2, 1, 2, 3, 2, 1, 0, -1. Will it match these? Oh, yeah. Do I have one too many? Oh, yeah, I do. That matches there. Okay. Thanks, Xcode. Okay. And let's clean this up. It wants this private closure spacing violation. Okay, sure. Oops. Yeah. All right. Run all tests 3 times. Okay. Well, that makes me happy. That's a moderately complicated expression. And in spite of all the swapping order and the spacing and whatever stuff, I mean, it did come up with the clustering we expected. Notice it's somewhat arbitrary because 2 and 3 you could have picked 2, 3 just as well as 1, 2 for the first one, but the algorithm's a little biased to go in order. So I guess that's okay. Right. All right. Now I wanted to make a change. Well, okay, let's check this in. I didn't really run it 3 times. Let's do that. Okay, and one more. Okay, so check full clustering algorithm, which still has some inefficiencies and all that stuff we're going to get rid of at some point. But I think what we have is an order n-cubed algorithm running on, well, the most we have is 39. So 40 cubed, 10 cubed is 1,000, 4 cubed is 64. So 64,000 whatever their countings for these things, probably comparisons. That's well within the range of what we'd expect to do. Okay, 100 gives you, is that 1,000,000 if I'm counting it right? So 1,000,000 is probably within the range of things. If you had 1,000, you're getting to, quite a bit larger. It may not be as feasible, but the algorithm we've done, I mean, it's order n cubed. We haven't optimized within the algorithm yet. And in particular, let's go up to our calculations here. We calculate this distance number. We're going to ask for the same thing over and over and over. And we would definitely be better off putting it in a table somewhere. I don't know the best way to do that, but it definitely would be worth it. It might, I don't know, hashing seems kind of expensive too, but we'll figure out something better that doesn't throw away all this information every time. If you're doing it 1,000,000 times and you could cut it down to, a handful of those, there's only, 40 times 40 comparisons, or possibilities. So it will help. Now, I'm okay with it like that. I know it can be improved. We definitely have taken the lazy way out on updating the matrix and not keeping track of the distances and so on. I call it a matrix, but all we're tracking is clusters. It's a simple list at this point. It really should be indexed by at n by n table, where it's the number of clusters, times itself, and distances for each one in the table. But we just have a linear list and we recalculate the distance every time. All right. Now I also know from this Wikipedia article, where they say C-link, S-link. Okay, yeah. So there's an S-link algorithm that has n squared and order n space instead of order n squared, I guess. It's old. I mean, what is that? 60 years old? Okay. And I'm just getting around to finding out about it. But cutting it down to n squared would be super nice. And we'll go from there. Okay. Since we went to all the trouble to understand this algorithm, let me find, so let's see, this rule, the minimum, so we take the two sets and whichever two elements are the closest in those two sets join the thing. There's other linkages. Yeah, so the complete linkage clustering, the difference is this formula, it was min xy. This one takes the max xy. So it's taking the furthest neighbor that's still in the cluster and pulling those in. So it's a little, that's going to have the effect of narrowing the clusters, right? Because you can't go as far to get something. So if you had a cluster that was this wide, trying to reach this cluster over here, well, you're going to come from the furthest away point, and so it's going to encourage maybe there's another cluster over here that's a little closer or something. So just another variation. And I think, we had our starting algorithm. I think it's just hierarchical. I might have gotten in there that way. That's single link. Single link. This one. Oh, yeah, there it is. So we're doing something in this family of linkages, and we're doing single link, which is min xy, and they're doing max xy, basically. But there are other alternatives, okay? Any of these kind of fit that same, well, many of these fit that same algorithm. So what's this one? Average linkage. Okay, you're kind of taking, you're taking basically the average distance between anything within these clusters, which sounds reasonable. And then this one's weighted average. I guess. Oh, okay. You're weighting it by the constituent clusters distances, which however those get computed, and so on. I mean, there's 10 or 15 or 20 variations here. Okay. Min of A and B, max of Y. Okay. The minimum of the maximum, or maybe the maximum of the minimums, all these possibilities. I don't think it's going to matter for us. I think if we get something that gets moderately plausible, then we're okay. Now, I do think there was one thing in here. It shows up in the example. So we're going to switch. We'll do a little refactoring first, but we're going to switch to this drawing the dendogram, this sort of picture of the hierarchy. So it's most of the world is not comfortable with reading lisp-style lists, and they didn't indicate any weight of how much it was, correct and stuff. You could go by nesting level, but this gives you a different measure. Okay, and if I look here, so they've done something where they said both C and E are plausible. They're equally far from A, B as each other. So if we look down here, it's going to be AB plus C and E. Okay, so they formed three elements in one cluster, the AB pair and the C and the E. And I don't think our algorithm actually will do that, because it's always finding the closest pair. So it's never going to do that, basically. Well, which is a little too bad. I mean, I don't know. We'll have to get some experience to decide how painful that is. But I can see the advantage to saying, D and E are basically equally far away from A, B, and they should be in the same cluster, All right. Okay, so we're going to understand this example and then see what we can do. Now, what I notice is we captured L as the distance between R and S. But down here, they do distance divided by 2. So there's a little disconnect. Whoever made the algorithm and made the example didn't quite look at it the same. So we'll take that into account somehow. All right. So we have the elements A, B, C, D, E. These are actually all bacteria. And we got pairwise distances. Okay. So he's going to cluster them and compute this delta function. Okay. So basically he looks for the smallest distance, which is A versus B. Okay. Well, is that right? D1 of AB is 17. Okay, that's the smallest number in the whole table except 0. And, okay, so cluster A and B together. All right, now we want to estimate something about their distance. We're going to say the distance of A to U, where U is the new node, is the distance of half the distance from A and B. Okay. I don't know what the ultrametricity hypothesis is. Okay, I guess. Well, I don't want to be ultra pseudometric. Okay. Well, so triangle inequality is kind of like the distance of any two sides has to be less than the other one. This one's restricting it even more. Some theorems are strange at first glance. Okay. Yeah, so ultrametric. So I guess we're promising some sort of strong distance relationship. All right. I don't think it's going to matter to us. All right. So A and B to U have lengths of this over 2. A and B to U. So I don't know where we'll keep that. Okay. Then update the new matrix reduced by 1 row and 1 column with the clustering. Okay. Bold values in D2 correspond to the new entries. Calculate by retaining minimum distance. Okay, yeah. And each of the remaining elements. Okay, so AB to C is 21, to D is 31, to E is 21. Okay. Now, AB to C, AB to E are 21. Cluster AB with C and E. Okay, that's what we won't do in ours. Now we want to estimate the length. The branches A or B to V and C to V and E to V are equal. Okay. Right. And that is the new number divided by 10.5 is 2, 10.5. I guess we know it's going to work because we're always taking out the smallest one. So the next one's going to be a little bigger. All right. We can deduce the missing lengths. Okay. Update D2. We've done that. Okay. Join the last cluster. Fine. The distance is 1/2. Okay. Now, where's the 14? Okay. So the 14 is the distance from the cluster, which is all this, and D, and so it's half the distance between them is the height. Okay. 14. But now we know the total distance, but we had to go backwards to get to the distance here. Okay. Now, our algorithm calculated distances, but it didn't do by half. So let's see what's going on in the algorithm. I guess I should say, if I had these distances, so if I had, if I had R to D is 14. How would I draw this thing knowing all these distances, even if I don't know? So the distance of A and B, so this 8.5, that was the first one, right? Yeah, we said 17. Okay. So we said this should be 8.5. Right. Okay. I almost wonder if we should be a set or not. Maybe it's a list. All right. I think if we gave you 8.5, we'd be fine, right? Starting here, we're building AB to U. We tell U your number is 8.5. That's your distance to the tip. Now V, oh no, that's weird. V is going to be 10.5 and R. Huh. Okay, so I guess each distance in a node is the distance to the tip. Okay, so if this node is 10.5, its distance to there is 10.5, but it's really too, well, this is the 8.5. How do you get to 10.5? You add 2. Okay, but the real thing is, I think we can put these distances in the nodes as we create them. We if the instance we're forming U, A, B, we know the distance of A and B. Now, the algorithm up there stored distance to A to B. Okay. I mean, I can see it maybe looks nicer if it's half the distance, but I don't think it changes it per se. All right. Now, I guess what I'm saying, we calculated L here, distance of R to S. They're saying take the distance divided by 2. I don't know if that, I'm not sure what that 2 is. I don't see how it would be any different if you took the actual distances, right? Because you had 17 plus 4 is 21, plus 10 is 31. And the last distance is 28. 17 plus 4 is 21. Plus 7 is 28. Yeah. It might cause it to stretch out less, but I don't think it changes the relationships. Okay. It's hard to be sure, but I think our algorithm is fine. We could scale that by whatever number as we drew it. It'd be fine. But I don't think it I don't see what the divided by 2 gives us here. We want elements A and B equidistant. I think that's a function of how we draw it, not. Well, a node's distance from the tip is 0, the initial nodes. Okay, so, all right. I think I have a picture. Okay. Oh, sorry, you had comments. Half because it's the average. I don't know. I don't think it's doing anything. Do we get the midpoint of the clusters? Maybe it is. Yeah, I mean, it is the midpoint of the distance to the clusters. You're right there. Trying to think if that gives us anything, though. What would that? I mean, if I used the half numbers, I have this thing. If I doubled them, they'd be longer, but I don't think they'd be different per se. But I don't have to do I don't have to do the halving on the way in. I could do it on the way out, I guess I'm saying, if it becomes important. And I don't know, I think it could be arbitrarily scaled and just make it squishier or not squishier, but the relationships are sort of the same. The distances are all multiplied. So, I mean, I forget what the statistical term is, but, they're numbers you can multiply to scale them. It's not like multiplying, degrees Fahrenheit and something's not really twice as hot if it's got twice as high a number. But these are measurements of length. And, if I do it on a 1 pixel per, 100 pixels per inch screen or 50 pixel per inch screen, it would certainly change the actual distance, physical distance, but I don't think it would change the relationships. 8.5 is still a little over half of 14. So, all right. But I think given the calculation we did here, we did update L, and we can do that with it. So now the question to me is, how would you draw a cluster? Can we draw a cluster kind of top down, I guess, right? I mean, okay, so suppose I guess we can take this one. I come in, I've got node R, and I know his distance is 14. And there might not be a single one of these that's exactly 14 because it could have been two separate clusters. But I'm going to draw a line from R's X position to the next one. Well, I think I'd be better off waiting, right? I should say, draw all your children, and then we'll draw you. And then I ask where, keep doing that, where that vertex is anymore. Okay. Yeah. So if I recursively go in and place the next two elements, place the next thing, draw the next one. All right. Well, he's got children. Draw your children. And you put these two in, you figure out your length because they're tips of the tree, you draw the full length. And then you say, yes, I put you at position X equals 8.5. I guess we got a backward scale, but okay. And then I come back. I guess he draws his children, then he places the letter, and it's going to take some, we got kind of an X and a Y to worry about. All right, but I think I understand sort of the thing. I mean, I think I can tell you, to draw something, you draw your children, that gives you their X coordinates, and their distance. I'm sorry, it gives you their Y coordinates and their distance. So the Y coordinate's kind of like halfway between them. I mean, the vertical halfway we can't escape, I don't think. All right. I think we can do something. I don't know if I'm trying to think it out in advance too much, but I do think it's like draw your children and then connect them. And how do you connect them? Well, you go to their Y coordinate, which is their average of their things, and you draw until you hit their distance. So you subtract your distance, like the 10.5 minus the 8.5 draws that 2. And then you find the coordinate of the C child, and he's 0, so you draw him all the way out. And E's 0, so you draw him all the way out. I think it can be done. I mean, I guess obviously it can be done, but I think I can do it. All right. Yeah, not clear why. Yeah, I don't know why. It may be, I mean, I can see an advantage to shortening it as much as you can that still makes the relationships visible. But, if I said, oh, it's 17 and I did inches, like, it's 2 pages worth of stuff. That's not very good. I think I may want to be able to scale the X coordinate, to make it fit on a page or a couple of pages or something like that. We'll see. I mean, I'm so little familiar with doing this stuff that I'm not super confident. But okay, so I said we refactor first. The one thing I know I got to do is pull this class out because that's just totally ridiculous. Okay, so we're looking for proximity matrix. And we'll put it in here with cluster. What the heck? Save myself once done. Yeah, I think we could divide by 4. I think we can divide by anything, honestly, and be okay. It may become, if I try to fit 100 things on one page, it might become so squished I couldn't read it. But I don't know. I feel like we'll learn. Let's see. I got an extra declaration up here. Yeah, don't need these two. Okay. Everything private and public, good. And then I can take this stuff out of here. I don't think I need algorithms in here. Undefined symbols. Hey, I got that this time. Oh, let's clean. I may have used some algorithm thing in here. Oh, or maybe I didn't have it in the other. Oh, here it is. Joined by. It's an odd thing to complain about. Oh, let's find this. Okay. Shared test. I think I can remove algorithms. But now I got to put it in these two. Target dependency, link binder with libraries. Well, maybe I only need one of those. Let's see. Okay, so I think I can take that out of here. Split out priority matrix dot swift. I don't know why the change when it accepted it the first time, but okay. All right. So I think our goal, let's see, do we have to do anything mathematically? I don't think we do. I think we've done it. We got those L values, distance values in there. And let's, so given a cluster, given a cluster, I think we can worry about how to draw this thing. I think we've got the computation done. Okay. Well, now we got some other work to do. Okay. I don't know how much to. Normally we've got to worry about the view and the stage. Okay, so let's add, we call it cluster. Sync, I guess I'm going to transform cluster. Okay. Let's look at the stage. Actually, which one's the most similar? It's probably, Parsons code, maybe. Or maybe sound view. Stage, okay. Whereas stage, we got to implement certain things. We got to do consume. Okay. So let's add a cluster stage. Well, okay, he's a transform. He's kind of like filter. It's not consume, it's transform. So I think I'm going to be like filter, that if you had this diagram or something like it, I'd like you to be able to click on either a node or one of these clusters. I don't know if it makes sense to click on a letter. This is one item. I definitely want to be able to click on these nodes, though. I could see selecting it, like dragging around a rectangle or something like that, but I think realistically, you'd probably look at something that was a certain size and take it. Click, 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 click on these intermediate ones and get the ones that are close. Okay. So I'm going to make, what's the transform? Gosh, it's a little like, average tune is complicated and slow enough that you had to actually ask for it. Usually we can just do stuff immediately, but I think we got to bring up a different window. So let's look at the view. Oh, it's a lot. I'm not totally happy with these. But okay, so we got the column names. Where's the window? Right, average tune view is the parent. It has a sheet, average sync view. Okay. I think we got to do the same kind of thing. So we'll need the basic view that corresponds to this. Okay. So, and I think the real thing is this, right? So we got to start with the stage. Okay. Oh, it's been a while. All right. Now, I think we've got some tests of these stages. Like there's filter stage test. But I'm not sure what the test is. I don't really care to check the sort of default stuff. But all right, I'm going to start and we'll see. Okay, I'm taking this junk out. Is a source sync or a transform? All right, now that should put some requirements on me. Maybe I've inherited enough. Okay, transform, I have to do this. Let's move this over. Oh, hey, I got a to-do list too. Let's close to the right. All right, we have a function that we have to do. Let's just return the input for now. All right. Override. Okay. And I don't know what that's about. I think it's an old message. Okay. Do I have other stuff? No. Okay. Oh, I hate it when I do this. I guess I'll just close that. Okay, to do. Use distance instead of similarity. Proximity matrix. Linkage function, nearest neighbor clustering. I think that's all the stuff we did the other day. It's a fourth. Oh, I didn't capture any of this yesterday. Okay, that explains it. April 5th. Okay, and this is all. Let's just call it clustering. Okay, and then today. April 6th. Okay, we did that test. Figure out clustering based on it. Yes, I guess that's sort of implied. Draw a dendogram. Okay, I think that's what we're working on. Create cluster stage and cluster view. All right. And then I do have to leave in just a few minutes, so we'll get what we get here. All right. He's neutral and I'm trying to remember how these things go. We need a view. And I'll take an easy one like statistics view. Okay. And I'm just going to copy it in for now. And just delete just about everything out of it. Cluster view. Okay. All right. So this is cluster view. I don't think we're going to need to know settings changed. We might. The stage is a cluster stage. Show report false. Okay. Stage type dot color. Okay, so he has a stage type. That's fine. They all do. That's based on this. Source transformation or sync. Okay. All right. Controls view. Well, I don't think we have much in the way of a controls view. I think we just have a button. Let's call it select. And I guess that says show report. We can get a better name. Let's call it show details. I think this is all we need. Statistics result. We don't have a statistics result. Well, name is, let's call it cluster. Icon name will come back to. Stage type is transform. Okay, let's run beta real quick here. We need to find something that says cluster. Could be some sort of nested container. Anything that looks recursive would be cool. Let's try shapes. That's pretty limited. Containers right out. Okay. Maybe stack. Square dot stack? I don't know. Square stack 3D up. Oh, what about something like this? Okay. I gotta have something. I don't have to be exact. Okay. Don't have statistics and cluster view. And what's cluster view take? Well, I guess he's got a stage. Stage. Okay. Where's this missing? Okay. I don't think I have enough here. Oh, thank you. Missing baseline 19. Yeah. Okay. Okay, I think we'll let that be it for today. I think the next piece is going to be hooking this cluster in. We have our overall pipeline, and I think, right, we'll need to make sure it's added to the list of active things. I don't know who calls this. Oh, the app. Okay. So we haven't fully defined that thing, but let's leave it to do here. So connect cluster stage to tune sim dot app. Okay. And I'll take this under what we did today. And we can break it out a little bit, I think. Okay. Well, like I said, I got an appointment in a few minutes, so I'll have to call it quits here. We'll pick up Monday, same time as usual, 2 to 4:30 p.m. Eastern or 6 to 8:30 p.m. UTC. Mudshark666, good to see you again. Thanks for your help as usual, and have a good weekend. Take care. Bye-bye.